This is a demonstration of the Balancing Chemical Equations interactive illustration from SciencePrimer.com. The illustration uses the oxidation of a variety of hydrocarbons to explore the chemical equation balancing process. A link to the illustration can be found in the video description. The illustration must be running to respond to user input. It is not running when the run button is light blue. It is running when the button is black. Once running, the main window shows a ball and stick representation of one molecule of a hydrocarbon, the name of that hydrocarbon, and a table with the number of atoms of each element present. The illustration uses only three elements. These are carbon, shown as black circles, hydrogen, shown as yellow circles, and oxygen, shown as red circles. When the illustration is first loaded, the molecule is methane. Using the topmost slider and switch on the right modifies the hydrocarbon. The carbon molecule slider allows the number of carbons in the chain to be adjusted from 1 up to 5. The alcohol switch adds or removes a hydroxyl group to convert the molecule from an alkane to an alcohol and back again. As the hydrocarbon changes, the name, ball and stick representation, and table also change. The next three sliders, labeled carbon dioxide, water, and oxygen, allow for the addition and removal of individual molecules of the other compounds involved in oxidizing or burning hydrocarbons. As the sliders are moved, ball and stick representations of these molecules appear and disappear across the top. The carbon dioxide and water sliders add complete molecules. For oxygen, the slider adds individual atoms. This means that a value of 3 on the oxygen slider corresponds to 1.5 oxygen molecules. Since you can't have half a molecule of oxygen, the illustration shows half molecules as one red and one faded atom. I'll say more about these half molecules towards the end of the demonstration. The last two buttons allow additional information to be toggled on and off. This information helps illustrate the equation balancing process. The Show Hide Equation button pulls up the hydrocarbon oxidation equation. Notice that it is not balanced, and when there are no molecules of a compound, the formula is shown in a faded blue. The prefix before each compound in the equation and the number of molecules shown across the top match and can be changed using the sliders. The final button, Show Hide Table, toggles on a table with a bunch of additional information. It lists the reactants, the hydrocarbon and oxygen, the products, water and carbon dioxide, the sum of the atoms present in the reactants, the sum of the atoms present in the products, and the difference in the number of atoms in the reactants and the products. Values in red in the last row mean the equation is not balanced for each of the atoms. The goal of balancing the reaction is to end up with the same number of carbon, hydrogen, and oxygen atoms in the reactants and products. Now, the best approach varies a bit based on the type of reaction being balanced. For hydrocarbon oxidation reactions, a good approach is to balance one element at a time, starting with carbon, then hydrogen, then oxygen. At the beginning of the balancing process, we start with just one molecule of the hydrocarbon, no oxygen, no water, and no CO2. In the table, what is present, we see only what is present in the hydrocarbon. In this case, we have ethanol with 2 carbons, 6 hydrogens, and 1 oxygen atom. These same values are shown as the sum of the reactants. With no water or carbon dioxide, the sum of the product atoms is 0. Following the order carbon, hydrogen, then oxygen, the first step is to add carbon dioxide molecules until there are the same number of carbon atoms in the products as in the hydrocarbon. In the case of ethanol, this is 2. With 2 carbon dioxide molecules, the difference between the product and the reactants is 0. The equation is now balanced for carbon. Next, add water to do the same thing for the hydrogen atoms. Watching this -6, we click on water, 1, 2, 3, until this value is 0. Now with 3 molecules of water, all of the hydrogens in the ethanol are accounted for in the water molecules. Finally, the excess oxygen atoms in the products are balanced by adding single atoms of oxygen to the reactant side until the difference in the third column is 0. So we'll add oxygen here and watch the value in this column. When the last row of the table shows all zeros, this equation for the oxidation of ethanol is balanced. What the equation says is that the oxidation of 1 molecule of ethanol requires 3 molecules of oxygen and will result in the production of 3 molecules of water and 2 molecules of carbon dioxide. In this case, the balanced equation has 3 complete oxygen molecules. For some hydrocarbons, methanol for example, one molecule of methanol combines with 1.5 molecules of oxygen to make 2 water and 1 carbon dioxide molecule. This 1.5 in front of the oxygen does not make sense when thinking about individual molecules. In order to balance this equation in terms of molecules, we can double all of the values. Doing this tells us that 2 molecules of methane combine with 3 molecules of oxygen to produce 4 molecules of water and 2 molecules of carbon dioxide. Another way to accommodate the 1.5 value is to change the units. If the equation is interpreted as showing moles of each atom or compound, it is perfectly acceptable to say 1 mole of methanol combines with 1.5 moles of oxygen to produce 2 moles of water and 1 mole of CO2.